Delaware Tech, Chemistry 100, Chemistry 110, Unit 4 continued. The effects of IMFs. There are multiple properties of molecular compounds that are really dependent on how strong the intermolecular forces are. Two of them on this slide are vapor pressure and boiling point, and they're together here because they're very closely related. The vapor pressure is the amount of pressure from a liquid that's producing vapors. It's producing a certain amount of it will become gas by evaporation, even at temperatures much lower than boiling point. So if I had a bottle of water and I just opened up the top, some of that water vapor from the liquid water, even at room temperature, would escape the liquid water and enter into the air. And that's vapor pressure. And the vapor pressure will be increased as you increase temperature, but let's talk about just keeping it at a constant temperature, room temperature. So at room temperature, you have a certain amount of vapor pressure, and the molecules that have weak IMFs don't hold those molecules in the liquid very well, and they evaporate very easily. So strong EMFs make it hard to vaporize, and therefore have low vapor pressure. Weak IMFs means it's easy to vaporize, and therefore it will be high vapor pressure. And of course, you can always make higher vapor pressure by just heating it up, because the molecules have more energy to escape their IMFs. It's the energy of the heat of the ambient temperature will be greater than the bonds that are in the IMFs, the IMF forces. Boiling point is the same thing, but you're heating it up so much that the vapor pressure has increased to the level where the vapor pressure coming out of the liquid, going up from the liquid, is the same as the atmospheric pressure pushing down in the liquid. And when those two forces balance, the pressure down from the atmosphere and the vapor up from the liquid, we call that temperature that gets to that point, we call that the boiling point. Now, you usually just represent the boiling point by, oh, it's the temperature where I see it boiling, but the technical definition is where there's so much vapor that it is able to completely counter the pressure pushing down from the atmosphere. So it's really just an extension of vapor pressure. The normal boiling point at 1 atmospheric pressure would be measured, and if you have stronger IMFs, stronger bonds holding that liquid together, it's going to be harder to boil. It's going to be harder to vaporize, so there'll be lower vapor pressure, and it'll be harder to boil, so it'll be a higher boiling point. Water is notorious for its high boiling point because of its very strong IMFs. In particular, its very strong hydrogen bonds. So if you look at this chart here, this is a chart of temperature on the y-axis versus the weight of the molecule, the molecular weight of the molecule. We haven't talked in detail about this, but suffice it to say that some molecules are lighter than others. And you know that dispersion forces get better and better as you increase the size, because they're able to polarize more of the electrons temporarily to form those London dispersion forces. And that's why you see this general trend up for each of the 4 curves. But you will notice there are 3 points on here that really diverge strongly from the general pattern: water, hydrogen fluoride, and ammonia. You would expect water to be down here. You would expect HF to be down here, and you would expect, let's see, ammonia in the green, you would expect it to be here. They would all be much lower than you expect. So why are the boiling points so high? Well, each of these has another IMF that is much, much stronger than this weak dispersion force. They are the hydrogen bonds. And we abbreviate hydrogen bonds frequently by calling them H bonds. That's a very common way to say hydrogen bond. Spell it out if you're writing a test, but if you said H bond, that would be perfectly acceptable. So these values pop up higher. So you see that the boiling point of water is much higher than expected by just dispersion forces, and that's because the H bonds, the hydrogen bonds, are so powerful that they bump the boiling point up to a level that's almost 200 degrees higher than we would have expected for other molecules like it, like H2S, H2SE, and H2TE, all in the same group of the periodic table, the oxygen group. erase these. Two more properties that are affected by IMFs. The first one is surface tension. Surface tension of a liquid is how strong the bonds are between molecules at the surface of a liquid. And we all know that water has a certain amount of surface tension. Some molecules have even greater surface tension. And we know that water has surface tension because there are insects like this water strider, or water striders can essentially walk on water because they're, first of all, very lightweight, and they spread their weight out with these very long legs that take advantage of the high surface tension, the high forces holding water together at the surface of the water. And this is very high because there are lots of IMFs holding the water together. In this case, it's because of the very strong hydrogen bonds again. So bugs can walk on water because of the high IMFs, making high surface tension. Viscosity is another characteristic of molecular compounds, where the velocity measures the resistance to flow. You can think of it as how thick the liquid is. We know that oils and syrups tend to be very thick compared to, say, water and gasoline. Gasoline has very weak IMFs, so it has very low viscosity. It pours very, very easily. Syrups are made with sugars dissolved in water. Sugars are extremely polar with lots of potential hydrogen bonds, and therefore they thicken up because there's so much interaction between the sugar and the sugar and the sugar and the water and the water and the water that they become very sticky and slow moving, and we call that high viscosity. So the higher the IMFs, especially with hydrogen bonds, which are even better than the other dipoles, and those are better than dispersion forces, they'll give you high viscosity. So the bottom line is high IMFs result in low vapor pressure, high boiling point, high surface tension, high viscosity. So let's look at some examples. We have four molecules here. CF4, that's a carbon tetrafluoride. NH3, nitrogen trihydride, but we know it as ammonia. Neon gas, and that just told you something. And phosphorus tribromide. Well, if you're asked what's the strongest IMF present in each, remember, if it can be polar, if it's a polar molecule, it can make dipole-dipole interactions. If it's polar and it has hydrogens on either a nitrogen, oxygen, or fluorine, that's even better. Those are hydrogen bonds. So hydrogen bonds are the best. Other polar dipole-dipole bonds are second best. And then dispersion forces are the weakest. So we can see right away by looking at this table that two of these molecules are completely symmetrical. Well, this one's only made of one atom. It's not a molecule at all. And this one is a very symmetrical carbon surrounded by four fluorines completely in a symmetrical fashion. So these are nonpolar. So we know right away, as nonpolars, they only have one choice, dispersion forces. And this one is smaller than this, so this is the weakest. Neon would have the weakest bonds. And we know that because neon is a gas. Just being a gas tells us that the forces are so weak it can't even hold itself together as a liquid at room temperature. Then we look at the others. We have this phosphorus tribromide, and if you knew how to draw the shape, that's fine, but you don't need to know. All you need to know is there's a lone pair here, which means it's nonpolar. I'm sorry, that it is polar. That's polar. And you know the same thing with the nitrogen, with its three hydrogens on it, also has a lone pair, and therefore it is polar as well. So which one's more polar? Well, we look at the electronegativity differences between nitrogen and hydrogen, and we look at the differences between phosphorus and bromine. These are higher. That's a higher difference. That has a high change, a difference in electronegativity. So our number one will be ammonia. Our number two will be this phosphorus tribromide compound, and then we're left with the much weaker carbon tetrafluoride and the even weaker and smaller neon gas. And I'll just erase this because the order is written here and with the names of each of the forces, and we'll just place them in the order. So neon is the weakest, ammonia has the strongest because it has actual hydrogen bonds in it. Whereas the PbR3 is polar, but it can't make hydrogen bonds, and the CF4 is a little bit bigger than the neon, therefore it has slightly stronger dispersion forces than the neon. So it's a lot of pieces of information you have to put together. First, you want to look for polar molecules, split the polar from the nonpolar. Nonpolar can only make dispersion forces, so they're at the bottom. Smaller ones are the worst. And then among the polar, you look for hydrogens on either a fluorine, an oxygen, or a nitrogen, and they can make hydrogen bonds. Those are your best choices for a dipole-dipole interaction. So, which of these pairs will have the greater surface tension? So, greater surface tension means better IMFs. So, we're comparing methane to water. Well, we know methane is symmetrical and therefore nonpolar, so it can't be that one. And water has strong hydrogen bonds, so we know it's water. Bromine is also non-symmetrical. It is symmetrical. It's totally symmetrical. It's just bromine attached to bromine, so therefore it's nonpolar. Symmetrical is symmetrical is nonpolar. Asymmetrical is polar. It gets very confusing. The opposites match each other. So that one can't be it because this one also has hydrogen bonds, so that's going to be much better, ammonia. And now we have two molecules that are very similar, silicon with 4 bromines and silicon with 1 bromine and 3 hydrogens. Well, when we have 4 bromines, and we know that's symmetrical, so that's going to be nonpolar, that's out. So our choice will be the silicon with 3 hydrogens and 1 bromine. And I'll erase those. And that leads us to a couple pairs of questions. We're going to look at the same pairs of molecules. Which of each of the two above has a greater viscosity? Well, it's going to always be the one with better IMFs. So it's the same set of answers, the water, the ammonia, and the silicon compound. And then the last question is, which one has the lower boiling point? Lower boiling point means easier boiling, which means poorer IMFs. Terrible IMFs mean it's easy to boil, it's easy to break apart. So low boiling point means low IMFs, and those would be the exact opposite choices, the methane, the bromine, and the silicon tetrabromide. And these are all nonpolar molecules. They're going to have lower boiling point. And that is the end of Unit 4.